So we wanted to have a last section. We went through the whole day thinking about principles and what those structures might be, and then we wanted to talk a little bit about different views of representation learning from the probabilistic perspective, what Jeffrey spoke about, and we wanted to have a little part about the neuroscience perspective on this representation learning problem. And so we thought Matthias would be the best person to give us that insight. He's been part of the machine learning community for a very long time. Many of you will remember him from deep art, neural art, which exploded, I don't even know, a few years ago. When was that? 2015?
Summer 2015.
Yeah, so time has gone by very quickly, and still continuing to help us think about what it means to do representation, neural networks, neuroscience, computational neuroscience. It's really great to have you. Looking forward to benchmarking machines against brain.
Thanks so much for this nice introduction and also for organizing this workshop. So I really like the mindset of the workshop. So as a computational neuroscientist / machine learning person, I really like the angle of representation learning, because as neuroscientists, we also try to understand what kind of algorithms the brain is using by looking at the representations. And I think ultimately it's about generalization. How can we build machines that better generalize, use data more effectively, use their resources very efficiently to make better decisions in the future. And so as a computational neuroscientist, I didn't feel very successful so far to understand how the brain is doing it. And so I got very excited when artificial neural networks started to do more and more interesting things. And now we should be in the position to have an advantage, right? Because we tried studying or understanding the brain, but it turns out it's not that easy to understand what deep neural networks are doing too. But another aspect is that we also think a lot about what are actually the right tasks that to study that learning systems should solve. And so I changed my title according to also Ferentz's introduction today. So I think my talk really focuses on this question: what tasks do we solve? And also maybe a little bit what principles help us to solve these tasks. I think I'm driven by similar intuitions that have been here in the room the entire day. And I will share my experience about them. So one keyword that comes up in representation learning is disentangling. And actually the work that you mentioned on style transfer was motivated exactly by this aspect of how can we disentangle content from style in image representations. So it's the spirit behind it is a little bit, it's not so much actually related to learning, but more if you think in the old days where we did demonstrations with the Fourier transform, and we combined images with the Fourier spectrum of an image with the power spectrum of another image. And then we said, okay, look, the phase spectrum is encoding the relevant information or the content of the image, and the power spectrum just contains noise. And these are two complementary types of image information. And in a similar sense, but now with more sophisticated shift invariant texture representations and high-level content representations, we have two somewhat complementary types of information that can be combined. And it's interesting that our visual system can cope with all kinds of variations in the image, so the texture information really dominates the pixel variability, right? Nevertheless, for these type of artistic images, you have to know Tübingen in order to know that these are all images of Tübingen, but you might be able to see it's always the same motive, even if you don't know Tübingen, right? And I think that's it's not a coincidence that we have this huge invariance against all these pixel variations, because there are many, many variations in lighting conditions and pose and so on that makes it really difficult to recognize things again in the world, because they never look exactly the same. And so the visual system had to find out a way to disentangle these different sources of variations. And I think that disentangling is basically the question of how to represent images in a way, or the sensory data in a way such that we in a task-independent fashion can reason about the world. Okay, this I skip. So if you want to try this out, you can use our app, of course, and can make nice images. So I have to do this little advertisement from time to time because I think it's still fun, actually. So we also, but as you can see, we try to go a little further in how we can disentangle even more aspects of perception. So instead of just having one aspect of content and one aspect of style, you can also say, try to disentangle the color information and say you keep the original color scheme and don't take it from the artistic image, but you only take the textual information from the artistic image, or you only take certain textures depending on different regions, so you might do some texture segmentation, or you might use texture information on different types of scales. However, I mean, it sort of works and you can generate nice images, but it's not like, say, the phase spectrum and the power spectrum of the Fourier transform. It's not that cleanly disentangling the information, but it's actually quite some compromising. So you solve an optimization problem and you try to find the best compromise, and in the end you have to cross fingers that it works. But it's also useful to as a tool to see to what type of image information are current ConvNets actually sensitive to. So one thing that you can do is you take an image from the ImageNet class with the label model T. Actually, Michael Black told me it's not a model T, but that's not my fault. It has been labeled by ImageNet like this. And you take an image labeled as a leopard, and then you use the leopard texture and impose it, or use that as a style and the model T as a content. And then you get something that looks a little weird, has some texture of a leopard here, but we would probably say it's rather a model T than a leopard, and the neural network thinks otherwise. But it's not that it always prefers textures. It also just do random things. So if you do color-preserving style transfer here with the lynx and the sable, then it thinks it's a stingray. So that's the winning class. So you can get all kinds of confusions in these neural networks when you introduce Q conflicts between texture and shape. And a master student of mine, together with Felix Wiechmann, a psychophysicist, wanted to study that in a bit more detail and used psychophysical experiment where you only have to distinguish 16 different types of class that are more easily to distinguish. And you can see some Q conflict stimuli here. So a cat with an elephant texture or a car with a clock texture. And if you compare the decisions of humans and machines, you can see that humans rely much more on the shape of the image, while the ConvNets usually are much more sensitive to the texture information in the image. So, in order to bring the brains and neuroscience in again, so how is visual decision making different between brains and machines? And so what I like about machines these days is that they have abstract neurons, so there are quite some similarities. And I do think of both as basically engines of intelligence. So we have a big artificial intelligence hype at the moment, but I find it quite important that the driving power behind it really is the ability to learn. So if you have a student that has done all the classes on the subject that is of interest to you, but is a slow learner, or you have another student who has just maybe 1 or 2 classes, but is a very fast learner, you tend to rather pick the fast learning student, right? Because in the end, the amount of intelligence or the amount of knowledge that you acquire about the subject is so much more dependent on your ability to learn than on the domain knowledge that you already have. And so I think we really need to make more progress on that. And I find it very exciting in some sense that we now have at least learning at a scale that it becomes relevant for practical applications. But the success criterion is really how efficient can we make use of experience to make good decisions in the future. And that, I think, or to me, means that how can we learn good representations of the world rather than of specific tasks. And the CNN revolution in computer vision started with a very specific task. So the ImageNet task that I already mentioned, assuming that everyone knows here about it. And a couple of years ago, we were still surprised that we can solve such a task where you can classify images from the internet into 1,000 different categories. And on this task, the performance now is estimated to be better than humans, even though this is maybe not the most careful comparison, but I think that in general, it's true for many, many tasks. If you stick to very fixed conditions where you test under the same distribution under which you trained your algorithm, you tend to outperform humans if you have had enough data to train your network. But how good are these CNN representations of the visual world beyond that task? And probably Lucas still remembers that when AlexNet won the image benchmark, I was still very skeptical and was saying, it's just overfitting on this task, and these representations are probably not very good. And so to me it came really as a surprise that when I saw the first paper coming out, well, the first that I saw at least, from Trevor this was too fast. From Trevor Darrett's group on transfer learning, using the AlexNet architecture as is, just learning different readout module on, I think, 6 other benchmark tasks and achieving state-of-the-art performance by using those features. So that is some evidence that these features are actually useful beyond the particular task that they have been trained on. And since I was so excited about this at the time, I tend to explain that more carefully. So the general idea of transfer learning is that you have a network, you train it with massive data, and then after to learn the feature space here, these are usually the convolutional layers of your network, and then in the most rigorous case, you just keep the conf layers and you only retrain the readout layers on a new task. So you steal those from the other task and then train with little data the new thing. And that was actually the first thing that we tried with neural networks in my lab, using originally the AlexNet and then later the VGG19 network on a task of predicting where people look in images. So there's the MIT benchmark, having something like a little more than 1,000 images that have been shown to subjects and recorded where the subjects look dependent on the image content. So for each image, you get a 2-dimensional heat map, and your task is to predict this heat map as a function of the image. And I don't go into details. We were actually the reason why we picked that task was because we were working on proper benchmarking, how much success we have made in the past on predicting on explaining the information that is in the data about the saliency, and at that time it was like 1/3 of the explainable information has been predicted by the saliency models. And then with this transfer learning trick, we actually managed to make very large progress by very little effort, so it's always nice if you don't have to work so hard for getting a big progress. So first using AlexNet, the explainable information became more than 50%, and then with the VGG19 network, it's even more than 80%. And so the main, we have also learned to optimize the network a little better, but to a large extent, this can be attributed really to the features of the convolutional networks trained on ImageNet. So at that time, I was enthusiastic about this experience that transfer learning works surprisingly well. But it's one thing to be surprised that transfer learning works and to have some anecdotal experience. And another thing to make this a goal, a success criterion of the modeling. And I think that's something I'm currently thinking about, how we can up with benchmarks to do that actually quantify how successful models are in feature transfer. And I haven't settled on a benchmark, so I should mention this. So I use you maybe also as a crowd to do some crowdsourcing. So my talk is basically suggesting a couple of tasks and aspects that I find important, but in the end, as you know, establishing a benchmark is not so easy, right? Because there are so many design criterions, you want to make it convenient and so on. And so any feedback is very much appreciated. So in 2016, you might have seen the Ubernet that basically also used this transfer learning paradigm, training, using the same set of features and training on, I think, 32 different tasks or more. I actually forgot, but it was a lot. I just show here 8 for which I could easily download an image from the internet. But again, it supported the general impression that these features are useful for all kinds of tasks, including surface normals prediction, boundaries, spectral embeddings, semantic segmentation, and so on. But how well and what kind of tasks allow better transfer and what kind of tasks are less easy to use these features is not clear. And so we particularly were interested in finding striking examples for which transfer may not work, and or say where humans are tasks which humans find easy and machines wouldn't work so easily. And one guess, so just an ad hoc guess, was maybe we do a closed versus open contour task, because closed contours are very salient to humans, and you can have a lot of clutter in the image and still you can recognize a closed contour and discriminate it from an open contour. And so the idea is that we will use the same type of approach. We will use the VGG19 features and then train a readout network, which basically consists on a pixel-wise nonlinear function. And the stimuli that we used here look like this. So we try to make it hard to make the distractors also being like little line elements and angles. But I guess you agree it's not so difficult for us to see the closed contours. And we made the way we constructed them was that we can basically have identical images with only tiny perturbations making the difference between a closed contour and an open contour. And in order to make things even harder, we also played around with superimposing nature image background. And this does make it harder also for humans. I think I can skip that. And here are the results. So for humans, we only measured with 100% contrast, so in the background, and with 0% nature image background. And interestingly, in these conditions, the CNNs actually were able to solve these tasks. And in this condition also the difference was not so big, so one can imagine with some additional optimization it might work. What is maybe more surprising, imagine you can solve this task, then probably you find it even easier to solve this task because the white lines have stronger contrast and otherwise nothing changed. So all we changed from the previous to this is now we have white lines on the background instead of black lines. And then what you can see is that human performance goes up quite substantially in both conditions. Interestingly, the model performance stayed the same or got a little bit reduced.
Is this a brief exposure? How long did you see this?
I think 100 milliseconds. So a brief exposure.
That's the question.
Yeah, you didn't look satisfied. All right. Okay, that's that. So then we learned about the SBRT dataset, the synthetic visual reasoning dataset, with 23 different problems, which are sort of similar in style to the ones we did with the closed versus open contour task. And in particular, we heard from Thomas Serres' group that the same versus difference type of problems should be difficult for machines and easy for humans. So the task is basically of this type that you get stimuli of two different categories, like here, category 1, you might have seen those stimuli, category 2, you might have seen those, and then you have to decide in the future, when you get new stimuli, how to classify the new stimuli. So if you see this one, you probably would put it into this box. And so humans can solve all these tasks very easily, so they get the task very quickly and are close to 100%. But machines do have difficulties. So again, we are using our transfer learning paradigm, but and now this is something that makes also these benchmarking kind of difficult. We fudged a little bit around with the readout. So we gave the readout a little more flexibility. So instead of doing 1-by-1 convolutions, we now do 5-by-5 convolutions so that the readout layer actually has a chance to compare things from different positions. Before, we only did point-wise computations in the readout, which was good enough for, say, saliency readouts or individual pattern recognition, but for same difference comparisons, I would have been also very surprised if it had worked with the other readout. And that, of course, makes this approach kind of tricky because if you put a large enough network on top of it, then it doesn't matter anymore what kind of feature space you have below, because then you have universal approximation properties and might solve the task anyway. But given that other people have tried to solve these 23 problems before, also without transfer learning, just as trying to solve them as good as possible, the result from Thomas Serres' group was that all the same difference problems seem to be harder than the other spatial tasks, spatial reasoning tasks. And there's an estimate of the human performance. And there have been there was another paper by Starbinger and colleagues using GoogleNet and LeNet, and so got sort of similar results. And yeah, our results on this, using this transfer learning paradigm. Interestingly, there are 3 problems on which we do better than without transfer learning, which is a same difference task where you basically have really identical objects at different locations, and that seems to work quite well. What didn't work, for instance, is a simple task, the same difference task where nothing is changed but the scale of the 2 different objects. So that might be the simplest task that couldn't be solved in this way, although one always has to be careful since we solve optimization problems, right? And maybe some more optimization tricks or some little tweaks in the readout might solve the problem. So I think in this anecdotal way, so far how we explored it, you cannot draw solid conclusions from it. It's more like a primer on which we hope to build a more principled way to evaluate these problems. But I find it quite useful to apply networks with the same feature space and a somewhat constrained readout space to a whole range of problems in order to get a sense for what type of problems are more difficult and which are easy. So I skip the other problems, so you can go through these different problems and reason about why some of them are more difficult than others. But the message here really is that I'm thinking about what would be a useful quantitative UberNet type of benchmark, and I think that's the important difference currently between brains and machines, that our brain really has to solve all kinds of tasks. And in machine vision, we usually assume that things transfer, but we don't try to build one network that solves all the tasks. Or maybe DeepMind does, but I haven't seen it yet. And another way how you can increase the range of tasks, 2 more minutes, okay, is to make networks more robust against noise. So you can introduce noise in the stimuli, and even tiny salt and pepper noise can change the classification. So this salt and pepper noise turns this classification into a broccoli. And we also, again, compared this between humans and machines, and it turns out machines are much more robust than a network that has just been trained on ImageNet. You may say, okay, you can still train a network also on noisy stimuli. Then you get superhuman performance again. But what doesn't work is if you train it on salt and pepper noise, it doesn't become robust against white noise or vice versa. So the question is how to train a network that it becomes robust against all kinds of low-level noise. All right, I have more that I wanted to show. So I think quantitative benchmarks are important, and benchmarks. I think we need to move into a domain where, like other types of generalization than IID generalization can be tested, and which look at data and resource efficiency. And I like to remind people that the brain only uses 20 watts and not lots of GPUs. We also do a lot of work on adversarial testing, and in contrast to, so it's not so much from a safety perspective, but more that to me it seems like a window maybe to benchmarking causality. And the idea behind it is that how well, it might be a way to test how well a network knows about the minimal necessary perturbation to change the state of the world, right? If you delete an object, then you should say that the object is not there anymore, and that might be the minimal perturbation that you have to do in a scene in order to get rid of that label. But that's not happening with neural networks as they are, but if you just look for the minimal perturbations, you basically get unnoticeable differences. And the way how this has been tried to solve so far is mostly by security by obscurity, so gradient masking, noise, some things that it becomes harder with the adversarial attacks that has been used in the past. But so I think it's good to try to make networks robust, or make this definition of robustness independent of the attack method that you use. So you should rather make the network robust against all possible attack methods. And that might be possible with a two-player game where you can attackers compete against defenders, and that's something we supported. And there will be a NIPS workshop coming up, a NIPS competition from July onwards where you can participate. And I still have half a minute according to my clock here, so I will use that. Just to make this point, because for many people adversarial examples are also kind of esoteric, right? It has a very practical meaning. Say you have a network that does good saliency prediction. And say you want to apply the minimal change to this image to change the saliency in a way that you want. For instance, you want, okay, we know that. You want people to look at this elephant rather than at these elephants. And if you just do this pre-image search, then you get an invalid result. So the model would think, so this image would almost be identical to this one. The model would think this is the saliency map, but the true saliency map, of course, stays the same. And so one question is, can we learn the minimal meaningful perturbation? So instead of doing just gradient descent, can we learn a restricted set of perturbations that lead actually to meaningful changes in the image? Okay, now I used up my time. Yeah, decision making of scenes in. I steal to 1 more minute. So one thing which might be surprising to you is that you can solve ImageNet with very tiny receptive neurons that look only at 16 by 16 patches or 32 by 32 patches with the same performance, say, as a VGG network. So it has no global understanding of the image, but all you need is to basically pool over lots of logits that you generated on all the possible patches in the image, and then you get very good performance. And this is also a way to then look at the images that are most make the biggest contributions to these classifications. It makes kind of sense, right? So it's also, we would say these are very contain a lot of information. But it's good to know that ImageNet can be solved actually with a bag of feature type of approach. So you use features like 16 by 16 patches or 32 by 32 patches, and those are descriptive enough to do this. And yeah. We can do also metameric stimuli. So these are 100% identical semantically, so they lead to exactly the same responses in the networks. But I shut up now. Yes, summary and my conclusion. We need quantitative benchmarks to measure robustness, data efficiency, and interpretability. Thanks so much for your attention.
Who wants to start the discussion? Any questions for us?
So you made it sound like you made it sound like the main reason, or the main thing that makes this transfer learning possible is the model architecture or the algorithm. So some architectures like AlexNet are this good at transfer learning, whereas BGG is slightly better or something like that. Do you think it's the actual deep learning architectures that we apply which enable that surprising transfer learning capability, or is it a quality of image not being such a useful auxiliary task for all the other things that we might want to solve? So is it something about the source task in this setting, or is it something about the algorithms?
Right, I think it's probably a mixture, which is probably an unsatisfying answer. So, I mean, people have tested also training on other data sets, and ImageNet turned out to be a particularly useful data set for transfer. Did you ask about specific properties of the architecture of the network that makes transfer possible, or?
I guess I just wanted to connect it to previous talks by Harry and others who said that one of the main important things if you use transfer learning is to choose your auxiliary tasks that you solve or your source tasks in such a way that are relevant to the target task.
Right. Yeah, I mean, it's obvious. I think it's pretty obvious that transfer should work better with those tasks. If you can imagine that they're using similar features, right? On the other hand, you can also train or do random permutations of the ImageNet labels and still get good performance, right? And that might also be an indication that these features are descriptive enough for the type of task that we are doing, but they are not doing the same thing as we do when we decide about what's in the image, right? So I think the mechanisms are quite different.
Okay, I think we can carry on.